The addition of variable frequency drives, or VFDs, can introduce harmonics into the power system. These harmonics can resonate with certain capacitor banks. The failed capacitors may have been resonant at a specific harmonic frequency, causing excessive voltage and current stress. VFD can generate heat, which can transfer to the capacitors. The new capacitors may have been installed closer to the VFD or in a poorly ventilated area, leading to overheating. The new power factor correction, or PFC capacitors may not have been designed to handle the specific harmonics generated by the VFD. The older capacitors may have had a more robust design or better filtering characteristics. Occasionally, capacitors can fail prematurely due to manufacturing defects or material imperfections. The new capacitors may have had a higher rate of defects compared to the older ones. Although the new capacitors were only installed recently, it's possible that they were damaged during shipping, handling, or installation. The older capacitors may have had a longer lifespan or accumulated less damage over time. The smaller, individual capacitors in the failed units may be more susceptible to harmonic damage than the larger, 3-unit design of the older capacitors. It's recommended to conduct a harmonic analysis to determine the presence and severity of harmonics in the system. Select power factor correction capacitors that are designed to handle the expected harmonic levels. If necessary, install harmonic filters to mitigate the potential for resonance. Ensure proper ventilation around capacitors to prevent overheating. Regularly inspect and test all power factor correction capacitors, especially after any changes to the system. When troubleshooting power factor correction capacitor failures, especially after installing new equipment like variable frequency drives, several factors should be considered. Firstly, the phenomenon of harmonic resonance is a significant concern. Variable frequency drives introduce harmonics into the electrical system, which are essentially voltage and current distortions at frequencies that are multiples of the fundamental frequency of 60 Hz. These harmonics can interact with the capacitor banks used for power factor correction, leading to a resonance condition. Resonance occurs when the inductive reactance of the system equals the capacitive reactance at a particular harmonic frequency. This can result in a significant amplification of voltage and current at that frequency, placing excessive stress on the capacitors and causing them to fail prematurely. The failed capacitors may have been particularly susceptible to resonance at a specific harmonic frequency generated by the VFD. Secondly, overheating is another potential cause of capacitor failure. Variable frequency drives generate heat during operation, and this heat can be transferred to nearby components, including the power factor correction capacitors. If the capacitors are installed in a poorly ventilated area or too close to the VFD, the elevated temperature can accelerate the degradation of the capacitor's internal components, reducing its lifespan and leading to failure. The new capacitors may have been installed in a location where they were exposed to high temperatures compared to the older capacitors, contributing to their premature failure. Thirdly, incompatibility between the power factor correction capacitors and the specific harmonics generated by the variable frequency drives is a factor to consider. Power factor correction capacitors are designed to operate at the fundamental frequency of 60 Hz and may not be able to effectively handle the high frequency harmonics produced by VFD. The older capacitors may have had a more robust design or better filtering characteristics that allowed them to withstand the harmonic distortion better than the new capacitors. It is possible that the new capacitors were not specifically designed or rated to handle the harmonic content present in the system after the installation of the VFD. Fourthly, manufacturing defects can also contribute to capacitor failure. Occasionally, capacitors may fail prematurely due to manufacturing defects or material imperfections. These defects can weaken the capacitor's internal structure, making it more susceptible to damage from voltage stress, current surges, or temperature variations. The new capacitors may have had a higher rate of defects compared to the older ones, leading to their earlier failure. Fifthly, age and previous damage could play a role in capacitor failure. Even though the new capacitors were recently installed, they may have been damaged during shipping, handling, or installation. Physical shocks, vibrations, or exposure to extreme temperatures can compromise the integrity of the capacitor's internal components, reducing its lifespan. The older capacitors may have had a longer lifespan or accumulated less damage over time, allowing them to withstand the operating conditions better than the new capacitors. Sixthly, design differences between the failed capacitors and the older capacitors can affect their susceptibility to harmonic damage. The failed capacitors had multiple small individual capacitors, while the older capacitors had 3 larger units. The smaller individual capacitors may be more vulnerable to harmonic damage due to their smaller size and potentially low thermal capacity. The larger units in the older capacitors may have been better able to dissipate heat and withstand the voltage and current stresses caused by harmonics. To address these potential causes of capacitor failure, several recommendations can be made. Firstly, conducting a harmonic analysis is crucial to determine the presence and severity of harmonics in the system. A harmonic analysis involves measuring the voltage and current waveforms at various points in the electrical system to identify the frequencies and magnitudes of the harmonic components. This information can be used to assess the risk of harmonic resonance and determine the appropriate mitigation strategies. Secondly, selecting power factor correction capacitors that are specifically designed to handle the expected harmonic levels is essential. Harmonic-rated capacitors are designed with features such as higher current carrying capacity, lower equivalent series resistance, and improved thermal management to withstand the stresses caused by harmonics. These capacitors are less likely to fail prematurely when exposed to harmonic distortion. Thirdly, installing harmonic filters may be necessary to mitigate the potential for resonance. Harmonic filters are designed to reduce the amplitude of specific harmonic frequencies in the electrical system. They typically consist of a combination of inductors and capacitors tuned to resonate at the target harmonic frequency. By reducing the harmonic content, harmonic filters can protect power factor correction capacitors and other sensitive equipment from damage. Fourthly, improving ventilation around the capacitors can help prevent overheating. Ensuring proper airflow around the capacitors allows heat to dissipate more effectively, reducing the operating temperature and extending the capacitor's lifespan. This can be achieved by installing fans, vents, or other cooling devices in the vicinity of the capacitors. Fifthly, implementing a regular inspection and testing program for all power factor correction capacitors is important, especially after any changes to the system. Regular inspections can help identify signs of overheating, bulging, or other physical damage. Electrical tests, such as capacitance measurements and dissipation factor measurements, can provide valuable information about the capacitor's health and performance. By monitoring these parameters over time, it is possible to detect early signs of degradation and take corrective action before failure occurs. Additionally, consider the system's overall design and operation. Ensure that the transformers are operating within their rated capacity and that the voltage levels are within acceptable limits. Overloading the transformers or operating at excessively high or low voltages can exacerbate harmonic problems and contribute to capacitor failure. Furthermore, proper grounding practices should be followed to minimize the risk of ground loops and other electrical disturbances. In summary, the failure of new power factor correction capacitors after the installation of variable frequency drives can be attributed to several factors, including harmonic resonance, overheating, incompatibility, manufacturing defects, age and previous damage, and design differences. By conducting a harmonic analysis, selecting appropriate capacitors, installing harmonic filters, improving ventilation, and implementing a regular inspection and testing program, it is possible to mitigate these risks and ensure the reliable operation of the power factor correction system. It is important to consult with qualified electrical engineers and technicians to properly assess the system and implement the appropriate solutions. This step involved in addressing the problem of power factor correction capacitor failure after the installation of variable frequency drives can be broken down into a systematic approach involving assessment, selection, mitigation, prevention, and maintenance. Firstly, the assessment phase involves a thorough evaluation of the electrical system to identify the root causes of the capacitor failures. This includes conducting a harmonic analysis to measure the levels of harmonic distortion present in the system. The harmonic analysis will help determine the frequencies and magnitudes of the harmonic currents and voltages, providing valuable information about the potential for harmonic resonance. The assessment should also include a review of the capacitor's operating conditions, such as ambient temperature, ventilation, and load profiles. Checking the capacitor specifications, such as voltage and current ratings, is important to ensure they are appropriate for the application. Physical inspections of the capacitors should be conducted to look for signs of overheating, bulging, or leakage. The data gathered during the assessment phase will provide a solid foundation for selecting the appropriate mitigation strategies. Secondly, the selection phase focuses on choosing the right components and solutions to address the identified problems. If the harmonic analysis reveals high levels of harmonic distortion, harmonic-rated capacitors should be selected. These capacitors are designed to withstand the stresses caused by harmonics and have a longer lifespan in harmonic-rich environments. The selection of harmonic filters may also be necessary to reduce the harmonic content in the system. Harmonic filters are designed to selectively attenuate specific harmonic frequencies, preventing them from causing resonance or damaging sensitive equipment. The selection of harmonic filters depends on the frequencies and magnitudes of the harmonics present in the system. The capacitors should also be sized appropriately for the load and operating conditions. Oversizing the capacitors can lead to increased costs, while undersizing them can result in premature failure. Thirdly, the mitigation phase involves implementing the selected solutions to reduce harmonic distortion and protect the power factor correction capacitors. Harmonic filters should be installed in strategic locations in the electrical system to effectively attenuate the target harmonic frequencies. The filter should be properly tuned and maintained to ensure optimal performance. Ventilation around the capacitors should be improved to reduce operating temperatures. This may involve installing fans, vents, or other cooling devices. The capacitor should be installed in a location that is free from excessive vibration or physical stress. Surge protection devices should be installed to protect the capacitors from voltage spikes and transients. Fourthly, the prevention phase focuses on implementing measures to prevent future capacitor failures. A regular inspection and testing program should be established to monitor the condition of the capacitors. The program should include visual inspections, electrical tests, and thermal imaging. Any signs of degradation or overheating should be addressed promptly. The electrical system should be designed and operated in a way that minimizes harmonic distortion. This includes using harmonic mitigating equipment such as harmonic filters and line reactors, and implementing good grounding practices. Variable frequency drives should be properly installed and configured to minimize harmonic generation. Fifthly, the maintenance phase involves ongoing maintenance and monitoring to ensure the long-term reliability of the power factor correction system. The capacitors should be periodically inspected and tested to verify their performance. Harmonic filters should be maintained and tuned as needed. Ventilation systems should be kept clean and in good working order. The electrical system should be monitored for signs of harmonic distortion or other problems. Any issues should be addressed promptly to prevent further damage. By following these steps, the problem of power factor correction capacitor failure after the installation of variable frequency drives can be effectively addressed, ensuring the reliable and efficient operation of the electrical system. Remember that consulting with qualified electrical engineers and technicians is crucial for proper assessment, design, and implementation of these solutions. Also, continuous monitoring and maintenance are essential for long-term performance and reliability.